Hey guys, good morning all. Just give me a yes in the chat if you guys can hear me and see the sublime text. Quickly give me a yes in the chat if everybody can hear me loud and clear and you guys can see the sublime text. Come on guys, be quick in the chat. Can you guys see it? Okay, all of you guys can see. Looks like there's some lag from my end. Anyways, coming back to it, this is our graph second class and I think we have a session scheduled for 4 hours. So we'll try to see how much we can continue and then we can take a break and then we can rejoin. Okay. Whenever you guys feel like you are tired or we should need a break, just let me know in the chat. We can take a break then and there. Okay. Let's see. We might not need to utilize 4 hours or we might need to utilize 4 hours or whatever date works. We'll see it out. Okay. Anyways, let's start with what you have done till so far. So our last class was on graph, which was yesterday. Let's see what we have covered so far. I think I've given introduction of graph already. The graph introduction is we have syllabus divided into two categories. One is basic, which is 70%. One is advanced, which is 30%. So basic includes theory, application, representation in terms of adjacency matrix, adjacency list, BFS detecting cycle in a graph, BFS and disconnected graph, DFS, etc., etc. And then we have the advanced, which is spanning trees, MST, perimeter square, and distance, which include Dijkstra, Bellman-4, and Floyd-Warshall. Let's go to what we have covered so far yesterday. As I always say, if you want to become master in data structure algorithm, what you need to know is you need to know three things about it. Number one, what is the use case or the problem that DSA algo is solving? What are its real-life application? How it is called or implemented? Number one, what is a graph? A graph is a finite set of vertices and edges which connects a pair of vertices. Three keywords I have highlighted here: finite, vertices, and edges. Finite means something which is countable. Vertices are the nodes in a graph. For example, in this case, 0, 1, 2, 3, 4, those are my vertices represented by the vertex V. Edges are the connections in the graph that connects the pair of vertices. For example, edges include 0 to 1, 1 to 2, 0 to 3, 3 to 4, and 1 to 4. Then we talked about types and classification. So the classification is based upon two types. One is based upon weight, other is based upon direction. So when we talk about based upon weight, we can classify into two categories, weighted or unweighted. A weighted graph means a weight or a cost is weighted with every edge in the graph. So if you look at this graph, with every edge, there will be a cost associated. And if you look at unweighted, there is no weight or cost associated with any edge in the graph. Then second category is based upon direction. So based upon direction, we have again two categories, directed and undirected. A directed graph means one way, undirected graph means two way. For example, if you look at this A to B, this is A to B path, this is a directed graph, this is what you call as unidirectional graph also. This A to B, there is no arrow here, means it's an undirected graph. So you can go from A to B and you can go from B to A. And if you look at this graph, this is bidirectional graph. So there is a path from A to B and there is a path from B to A. This is what you call as bidirectional graph. Bidirectional graph pretty much behaves like the undirected graph. So the graph that we have considered so far, it is undirected and unweighted. Then we move to the applications part of it, where graph use, what are its real life applications. So multiple applications of graphs in our real life usage. Number one is the navigation services. Any kind of navigation service that you use, which includes Google Maps, Apple Maps or something, all of them use a graph. Let's see how we use it. Imagine if this is a weighted graph and then you have some vertices and some edges which are denoting the distance or whatever field that you want to denote here. Let's say 0 and 4 are two cities, which are the vertices in my graph. And these edges weigh 10, 15, 5, 27. These are denoting the number of minutes or number of hours it takes from one city to another city. So if I ask go from one city to another city, it will tell me all the ways and it will show me the minimum number of hours or minimum number of minutes I need to do to commute between the two cities. That's one example. Second example is networks and topology in computer networking. For example, if you have 10 servers and you need to connect them in star topology with minimum cable length. So here my vertex or nodes are denoting the servers, edges are denoting the cables. So if I convert this into a graph question, it will be a graph with 10 vertices. Return the minimum length connecting all the vertices. That's what the question will become in terms of graph. Third and the most important is any kind of recommendation system or in general the social media. So we talked about three use cases. Any social media that you use, including Instagram, Facebook, Snapchat, the first is a direction. So if I draw this kind of a graph, so A is connected with B, B is connected with A, C is connected with B. Now, if in Instagram, so what is denoting is A or the vertex are denoting the person or a page, and this edge is denoting a follows direction. So A follows B, B follows A, and C follows B. Now, how you can relate in terms of real life example, the product, you can relate with Instagram. So in Instagram, if one person follows another person, the other person may or may not follow back, right? So here you can see A can follow B, B may or may not follow back A. This is directed graph. In Facebook, when two nodes are connected or two person, two accounts, that's what I'm calling as node are connected, both follow each other, that becomes a directed graph. Okay. Then we have the second category, which is connectivity. What do you mean by connectivity? So A is connected with B, B is connected with A is not connected with C, right? So when A will visit the profile of C, it will say that you have mutual friends with B. Then you have personalization or degree of connectivity. What is personalization? We have something called closeness score. Closeness score determines the closeness of connectivity between the users. It depends on multiple factors and matrices, which includes like your engagements with them, likes, comment, share, tagging in stories, etc., etc. All of these closeness score will contribute to a number, right? For that number, whatever number will be higher for a person, we are going to more likely engage with them. So for example, the score of B with A is 100, score of B with C is 10. So if I show the post of A and C to B, B is most likely to engage with the A post because their closeness score is high. Then we move to the last part, which is coding and implementation. Before the actual coding and implementation, it's something important to understand about representations. There are two categories of representation, adjacency matrix and adjacency list. And even before we go there, what is representation? Representation means any piece of information, if I give you that, it is sufficient to redraw the graph. That is called the representations. For example, if I talk about adjacency matrix, the word says it's a matrix, there's going to be a number of rows, there's going to be a number of columns. So it has V rows and V columns. So it's a V cross V matrix. If a direct path exists, you put the value 1. If it doesn't exist, you put the value 0. So this is how your current graph looks like. If you have to make adjacency matrix out of it, how will I make it? I'll make a V cross V matrix, which is 5 cross 5 matrix. If there's a direct path, I'll put the value 1. Otherwise, I'll put the value 0. So this is what my matrix will look like. Now, something important about this matrix, I took this matrix out. Two things to observe in this matrix. Number one, all the diagonal elements are 0. Diagonals are I, I coordinates. So I, I is 0 means there is no self-edge on any vertex. Second, if across the primary diagonal I make a cut, it will be symmetric. What do you mean by symmetric? The transpose of this matrix is same. It means it is an undirected graph. Why? Because when you say A to B is connected in undirected graph, B to A is also connected. So any undirected graph, its adjacency matrix will always be symmetric across the primary diagonal. Complexity becomes big of E square. That is first representation. Second representation is adjacency list. What is adjacency list? It's the array of list. What is the size of that array? That is number of vertices. So for this graph, if I have to make the adjacency list representation, how will we make that? Adjacency list denotes for a one particular vertex, what is the list of directly connected vertices with A? Okay, so it's a structure like this. The key is a vertex and the value is the list of directly connected vertices. Now, if I start with 0, what are directly connected vertices with 0? It's 1 and 3. If I talk about 1, it is 0, 2, and 4. If I talk about 2, it is 1. If I talk about 3, it's 0 and 4. Let's talk about 4, it's 1 and 3. Okay. How do we represent a weighted graph and adjacency list? So for weighted graph, along with this, we'll write a weight as well. So let's say for 0 to 1, the weight is 10, something like this. We'll present it like this. In that case, it will become a pair. So 1, 10. That will become in terms of a weighted graph. Okay. Anyways, coming to next, the complexity becomes a big of V. So one advantage is we are able to reduce the complexity from big of V square, which is an adjacency matrix, to big of V, which is adjacency list. However, there is one con. There is one edge case where adjacency matrix perform better than adjacency list. What is that edge case? If you're provided the adjacency matrix and adjacency list, so the complexity of creation of matrix and list is not taken into picture. You're already provided that. And then you need to check if direct path exists between source and destination. In that case, adjacency matrix will just take big of 1 complexity. In adjacency list, in the worst case, you have to go for big of V. You might have to go through all the vertices, provided one vertex to connect it to all other vertices. Okay. Then finally move to the code part. So in terms of code part, as I said, we are going to write the adjacency list because adjacency matrix is expensive to code. It's big of V square complexity. We're going to do the adjacency list. Now there are, in all the languages, there are two ways. Either you can use something which is given by the language like STL collection framework or using a module, or you can write a custom class for graph and then you can code it. The way that we are going to code it, the number one, I chose the language Python because it's first easier to understand what are we coding and then we can switch to other languages. In Python specifically, I first started with normal dictionary. So we realized in normal dictionary, the kind of pattern that we look, we need a key and we need a list of values. For beginning, I need that key, but I want the list of values to be empty because I have not traversed it. Once I will traverse it, then I'll get to know what are directly connected vertices, then I can fill it, right? So as of now, I have a key and I have the empty list of directly connected vertices. So in a normal dictionary, if I don't have a key present, then in that case, it will give me a key error. So normal dictionary won't work. And then there is something called default dictionary, which is available in the collections. In that default dictionary, if that key is not present, at least it will not give me a key error. It will give me whatever value I want to pass. So if I pass a list, it will give me an empty list. And that's exactly what I need. So adjacency list, the kind of structure that I need, one vertex and an empty list because I have not actually traversed the graph yet. Once I traverse the graph, then I'll fill whatever that list is. So if any vertex is not visited yet, instead of throwing key error, I need an empty list along with it. Hence, I use default dictionary instead of normal dictionary. And finally, we write down the code for a graph. So this is the graph. Basically, we just create default dictionary by a list that becomes a graph. Then we have a function called add edge. What are we doing in that add edge? From a graph, we are adding up edge from source to destination and destination to source. So that becomes a undirected graph. If I comment this line, it will remain a undirected graph. Okay. Then we create an add edge for this graph. We printed that, and if we also do it for a directed graph, we printed that, and everything works fine. We know the time complexity, which is big of V. This is something that we have done till last class. Today, we are going to start with traversal. But before I start with that, quickly give me clear if everybody crystal clear with the revision. Any doubts, any questions, please let me know. Come on, guys, be quick in the chat. All good? All right. If everything good, let's go to traversals. All right, number one, as we know, that graph is a hierarchical data structure. What do you mean by hierarchical data structure? There is more than one logical way to traverse. So how we're going to traverse, it's not just one way. It's not like you can say left to right or right to left. It's more than one logical way to traverse. There are two ways. One is called BFS, one is called DFS. Similar in trees as well and in tries as well. BFS means breadth first search. DFS means depth first search. Okay. There are two ways you can traverse it. Now, what is this BFS, DFS? Obviously, we have seen in terms of trees as well. So I'll try to make an analogy with trees and then we'll see it for the graph. Okay. The logic of BFS, DFS remains same irrespective we are doing it in a tree or in a graph or in a trie or any other data structure. Algorithm will not change the logic based upon a data structure. Remember that line. Okay. So let's first try to relate what have we seen in terms of trees. Let me quickly make it a tree. 0, 1, 2, 3, 4, 5, 6. A simple binary tree. If I ask you to do a BFS traversal, what is the output? If I ask you to do a BFS traversal, what is the output? Quickly in the chat. Come on, guys, we just completed trees. Quickly in the chat. Correct. The BFS traversal will be 0, 1, 2, 3, 4, 5, 6. You'll go to each and every level and you will travel left to right. That is what you call as BFS or level or traversal. What is the concept behind it? The concept behind it is if you are at 1, let me put it this way. The logic of BFS, DFS, as I said, the logic of algorithm will not change as per data structure. The logic will remain same. The definition will remain same. If you're currently standing at 1, you have two choices. Either you can go to the depth or you can go to the breadth. Your depth is either 3 or 4, your breadth is 2. If you go to the depth, that is called depth first search, DFS. Okay. If you go to the breadth, that is called the breadth first search or BFS. This statement clear to all? This statement crystal clear to all? Okay. That is the definition of DFS, BFS, nothing else. The word itself, DFS, BFS tells you what they are doing. If you go to depth first, you call it DFS. If you go to breadth first, you call it BFS. Same will remain everywhere, irrespective it's trees, graph, tries, whatever. Okay. So I'm going to clear this, come back here, put it here. Let's see. If you select 2, that is what is called as BFS because you choose adjacent or breadth here. If you select 3, that is called DFS because you choose children or depth here. Okay. In a graph, we don't call children, but in tree, we can call the children. Same logic if I do it with tree. The same logic if I do it with graphs with whatever I have done with trees. The logic will remain same. If I come to explanation using graphs, let's have a look. How do we define the depth and how do we define the children and adjacent? Because there's nothing called children in a graph. There is adjacent, but there's nothing called children there. So how do we define that? Let's talk about it. If you cover all the directly connected vertices directly connected vertices. Directly connected vertices is something we call as adjacent vertices or the breadth. And you don't go to any other vertex. This is what you call as BFS or breadth first search. If you don't cover all, the word all is important, the directly connected vertices, those are adjacent vertices, and you go to any other vertex, that is what you call as DFS, depth first search. Okay, this is the explanation using graph. If you are at a current vertex and you have directly connected vertices with this, that is what you call as adjacent vertex or breadth vertex. If you cover all of these adjacent vertices, which are directly connected vertices, and you don't go to any other vertex, that is what you call as BFS, breadth first search. You covered all the breadth first. If instead of doing that, before covering all of them, you go to any other vertex, that is, it is called as depth first search because you choose a depth. So DFS, depth vertex is traveled before completing all adjacent vertices, which is breadth. So DFS, the depth vertex is traveled before completing all adjacent vertices. That is what you call as DFS. Okay, let's try to understand this with the graph that we have been using so far. I'll take one of these graphs that we have been using so far. Let's take this guy. Okay, let's do BFS, DFS here. Now, one thing, in a tree, we know the traversal will always start from a root because there's a fixed root, then there are children, so on and so forth. In a graph, there is nothing called root because there's no children, nothing like that. A graph does not have any hierarchy, right? So how do we decide where we have to do? We choose a particular vertex to start our traversal with. There is nothing called graph here. There's nothing called root here in the graph. Okay. So let's say I define my source and I can choose any vertex that I want to travel from. I choose the vertex 0. If I start with 0, can you guys tell me what are the directly connected vertices with 0? Quickly in the chat. Come on guys, quickly in the chat. Directly connected vertices are 1 and 3. That will become my breadth. Okay. So directly connected vertices, that is what you call as adjacent vertices, that will become your breadth. So if I start my traversal from 0, if I cover both 1 and 3, and then I go to anywhere, that will be called as breadth first search because I completed my breadth. If before completing both 1 and 3, I go to any other vertex, that will be counted as DFS because I didn't cover my breadth first. Okay. So 0, 1, 3, and then you travel whatever you want to travel, or 0, 3, 1, whatever order you want to do, then you travel whatever you want to travel. That is called BFS, breadth first search. But let's say I go from 0, 0 to 1. From 1, I move to 2, and then I'm doing whatever I want. Or similarly, I go to 0, go to 3. From 3, I move to the 4, and then do whatever I want to do. This will be called as DFS. This is the definition of BFS and DFS in a graph. For a vertex, find the list of directly connected vertices. If you cover all the directly connected vertices before going anywhere else, then it is called breadth first search, BFS. If before covering all the directly connected vertices, you go to some other vertex, that is called DFS, depth first search. Everybody crystal clear with this? Come on guys, quickly in the chat. Everybody crystal clear with this? Okay. I'll give one more example. I have explained this part. I will take another example and I'll give it to you guys to solve it. Okay, then we'll write the code. But before that, one more important thing. Although it is clear how do we do DFS and BFS, one thing is important is in a tree. Okay, you guys tell me before I tell you guys. What's the difference between a tree and a graph? What is something a tree cannot have and a graph can have? Let's start with this. What is something a tree cannot have, but a graph can have it? One guys quick in the chat. Correct. Not the bidirectional. Yeah, technically bidirectional is what you're saying. The thing is that graph may contain cycle, but trees cannot have a cycle. The moment trees started having cycle, they'll become a graph. So when we are doing a cycle, why did I particularly mention about cycle? When we are doing a cycle, we need to track wherever is a cycle. Otherwise, we'll never be able to complete. What am I saying? Look at this. Let's put it here. Let's put it here. If I talk about traversal of this one, right? I have to do traversal. I start from 0, then let's say I go to 1, let's say I have 4, then I have 3. If I don't keep a track of the vertex I have visited, I will always run in an infinite loop. For example, 0, 1, 3, 4, 0, 1, 3, 4, 0, 1, 3, 4, 4, 3, whatever that is, and so on and so forth. And I'll keep on traveling in this infinite loop. So since my graph can contain a cycle, I need some kind of mechanism to figure out which vertex I have already traversed. So if I'm traveling it again, I will know that I'm encountering a cycle. Agree? Think of the linked list. When linked list has cycle, we did that question, right? When I'm doing a cycle, when I'm going through a cycle, I need to track which vertices I have already visited. If it is already visited, I don't need to visit it again. Okay. So I'll just clear it. I'll come back here. Since graph may contain cycle, so what do? Avoid visiting same vertex again and again. We keep track of number one, either using a Boolean array or set for visited vertices. Okay. So since a graph may contain cycle, so to avoid visiting same vertex again and again, we either keep track of using a Boolean array, whether it is marked visited or unvisited, or we set for the visited vertices. Either you keep a set or you keep it an array, whatever works. Now, since we are clear with the definition of BFS and DFS, now I'm going to take you an image and you guys are going to tell me about the BFS and DFS from wherever we start with. Let me find that image for you guys. Quickly give me a minute. Then we'll take on the next part. All right, here it is. Let me quickly share my screen. Okay. Can you guys see a graph here? Quickly give me answer in the chat. Can you guys see a graph here? All of you guys can? Cool. If you guys can see a graph, let's start noticing this graph a bit. Number one, is it a directed graph or undirected graph? Obviously, you can see the arrow. So this is a directed graph. Okay, makes sense. Is it a weighted graph or unweighted graph? This is unweighted graph. So this is directed and unweighted graph. How many vertices? How many edges? How many vertices? How many edges? Correct. The number of vertices are 4 here. And the number of edges is a how many? Let's count it. 0 to 1, 0 to 2, 2 to 0, 1 to 2, 2 to 3, and 3 to 3. So total 6 vertices. So it's directed and an unweighted graph, 4 vertices and 6 edges. Okay. Let's say I start at 2. What would be my BFS traversal? What would be my DFS traversal? That's something you guys have to tell. But before I go there, let me take you back to Sublime Text and then I'll give you enough time. Okay. So for this graph specifically, directed and unweighted graph. Number of vertices are 4, number of edges are 6. Starting vertex that we are keeping at 2. So starting with the vertex 2, you guys need to tell me what is going to be the BFS, what is going to be the DFS. Okay, that's going to be our task. Any doubts in the question before I go? I'll give you a time, I'll show you the graph. Any question before that? You know the graph, you know the starting vertex. Starting from 2, you need to tell me what is the BFS output, what is the DFS output. So from everyone, I need this kind of input, BFS and DFS, whatever your output will be. Please change a message directly to me. Do not message to everyone. Let everybody think and comment, and we'll discuss. Okay. Here's a graph. Let me pull the graph. There you go. Here's a graph right in front of you. Starting vertex is 2. Starting from 2, tell me the BFS and DFS output for this graph. Please change your message directly to me. Do not message to everyone. Let's target 30 seconds or 1 minute at max. I don't think it should take more than that. Once you guys are done, let me know in the chat, then we'll discuss. Your time starts now. Already has enough time. I think majority of you have given the answer. Let's start discussing now. Okay, enough time for this. Cool. Let's start with BFS and DFS one by one. If I start with starting vertex 2, and let's first talk about the BFS traversal. Okay, BFS. What are directly connected vertices with 2? What are the directly connected vertices with 2? Quickly in the chat, guys. 0 and 3. So 0 and 3. If I cover this 0 and 3 in any order, that will become BFS. So 2, 0, 3, 1, or 2, 3, 0, 1. Both will qualify for BFS, breadth first search. All agree with this? All agree with this? Yes or no? Come on, guys, quickly in the chat. Okay. If I talk about DFS, DFS means if I don't cover both of them, instead I move to the depth of any of them, that is called DFS. So if I go to 2, let's say I go to 0. After 0, I go to the depth of 0, which is 1. So I go to 2013. Now that will be called as DFS. So DFS output 2013, BFS output 2031 or 2301. All agree with this? Come on, guys, quickly in the chat. All agree with this? Okay. If everyone agrees, let's clear this first. Go back here. Let's write it down. Then we can write the code for DFS. Let's go here. Here we are. Okay. First thing first, starting vertex is 2. We need to point out the directly connected vertices. Directly connected vertices for 2 are 0 and 3. One moment. For 2 are 0 and 3. So BFS will become 2031 or 2301. DFS, I can start with 2, 0, go to the depth 1, then 3. That is the correct answer. How can one go 3 since there is edges connecting them? No. Okay. Understand one thing. When we talk about traversal here, it doesn't necessarily mean we have to follow in the same direction. So when I'm saying 2, 0, 3, 1, that doesn't mean that I'm going from 2 to 0, then 0 to 3, because there is no edge from 0 to 3. We just type about traversal like how many vertices we have traveled. That's it. If we cover them in the same, then we call this BFS, otherwise we call them DFS. This order does not directly mean the order in which I'm traversing the graph. Okay. Clear this. I'll come back to Sublime Text. There you go. Okay, here we are. Now coming back to this. This is what we've understood from the traversal of BFS and DFS. I've explained the explanation using trees. BFS go to the breadth first, DFS go to the depth first. What do you mean by breadth and depth here? Breadth means the directly connected vertices. Depth means if we don't cover all the directly connected vertices, if we move to some other vertex, then it will be called as DFS. Okay. Now let's move to the code part. We'll start writing the code. We'll see the code for BFS first. So let me start with lead code real quick, and then we can do it. All right, we are back on lead code. Let's quickly start coding here, whatever language you want. So first thing, from collections, let's import default dictionary. That's something we have become understood by now. I'm going to create a class graph here. What am I going to do in that? First, let's make a constructor for self.graph is equal to default dictionary passed by a list. That's become my graph. Okay. Please direct it to itself. Don't we consider that? See, that's what while we are doing the traversal, that's what we do. Since it's making a cycle, we'll not be traveling it again. Otherwise, if you travel that, so there will become infinite 3, 3, 3, 3, 3. That's the logic that we have to take care of the traversal. That's what I pointed out. If there is a cycle, we use either a Boolean array or we use a set. Okay. Now, I would need a function called addEdge to add edge. That's something we also know. So source, destination, that's it. And then I will need a function for BFS. For BFS, I would need just a start. That is how the structure of my graph will look like. Now, after this, outside this, I can create an object of this class, g equal to graph. In my graph, I can add the edges. Okay. So let's see. 6 edges, right? 2, 3, 4, 5, 6. So my graph had 6 edges. Let me open the graph again. 4 vertices, 6 edges. That's what we discussed. This guy. So what are the 6 edges? Let's make a count. 0 to 1, 0 to 2, 2 to 0, 1 to 2, 2 to 3, 3 to 3. Okay. Let's write down those 6 edges here. What do we do? First, 0 to 1, then 0 to 2, 1 to 2, 2 to 0, 2 to 3, and 3 to 3. That's it. After that, I want to print, let's say, BFS from 2. Okay. What do I need to do? I just need to do g.bfs. I'll pass the value 2. This is what the structure of code of my BFS will like. So I'll write some logic in my class graph. Basically, I need two functions. Add edge we have already done in the last class, which was yesterday. I just need to define a logic in BFS. Then I can create a object of the class graph. I can add these edges, 6 edges, and I can do the BFS from 2, expecting that I'm giving 2 as the starting vertex. It will give me the BFS output. Everybody clear with the structure of the code first? Everybody crystal clear with the structure of the code first? Come on, guys, quickly in the chat. Super easy, right? Add edge we have already done. We're just going to define a function BFS, which is taking a starting vertex and passing the starting vertex. That's it. That's all we need. Now coming to actually implementing the code. The add edge part, we have done it yesterday also. What we need to do? This is a directed graph or undirected graph? This is a directed graph or undirected graph? Quickly in the chat, guys. The graph that we saw is a directed graph. So there will be one edge connected, not two edges connected. Okay. If you remember from the last class, yesterday, I mentioned about this. Source to this would be the initial one. And when you write like this, graph of source dot append destination, means now in that list, you're appending the destination. Agree? Now in that list, you're appending the destination. That's what you're doing. Now coming to the code part. First thing, graph source dot append destination. That's all that I need to do because it's making a path from source to destination. Should I add for destination to source also? Should I add for destination to source also? No. Why not? It's a directed graph. So this is fine. Then we move to next, which is the BFS, and this is the code that we need to follow. Now, first thing first that we need to follow in BFS is, as I said, that can contain cycle. So I'm going to mark everything as not visited. Falls into max of self.graph plus 1. Then I create a queue, which is empty, just to make sure which particular vertex I have traveled so far. I am going to start with starting vertex. First thing, I'm going to mark the starting vertex as trip. Now what next? While my queue is not empty, what am I going to do? My current vertex will become queue.pop0. I am going to first print the current vertex. Something like this. Print the current vertex. Now what? In my adjacency list, let me write it down here. In my adjacency list, it should be current vertex and its neighbors, or the list of directly connected vertices. So what do I need to do? I need to iterate over directly connected vertices. of what? Of current vertex. That's what I need to do. How will I do that? Let's see. For neighbors in self.graph current vertex. If I do graph current vertex, means that will give me a list of edges or list of vertices. Those list of vertices are directly connected vertices. Okay. What do I need to do? I need to check if they have been already visited or not. So if visited of neighbor is false. If it has not been visited, then add it to my queue. You dot append that neighbor and mark that as visited. Neighbor go to tree. That's it. That's all I need to do. Okay. Let's go through the code again. This is just a constructor initializing the default dictionary. This is add as directly connected vertex. That's a directed graph. Now in the BFS, what am I doing? Marking everything as not visited, creating a queue to track it, appending the start to the queue, marking the starting vertex as visited. While my queue is not empty, I got my current vertex, append the current vertex. I'm going to a directly connected vertices of current vertex. If it is not visited, then I'm visiting it and I'm marking it as true. Everybody crystal clear with the code. Come on, guys, quickly in the chat. Everybody crystal clear with the code. It's super easy, guys. Let me know. Any doubts, any questions, please let me know. Easy. Okay, let's run the code. What is the expected output? It looks same as tree pre-order. Tree pre-order, we don't maintain a queue in a pre-order. You mean the BFS of a tree? Pretty much yes. If it's a BFS, yes. Now, what's the expected output that I'm expecting here? I'm expecting the output here. Remember, it was what? 2031 or 2301. Let me take it back. We're expecting this. Either it should be 2031 or it should be 2301. Let's run the code. Let's see the output. Name neighbor is not defined. Do you mean neighbors? Line number 26. Line number 26. What did we miss? Line number 26. If visited, yeah, that should be one neighbor, not multiple neighbors. Okay, what do we get the output? We get the output 26031. Means my code is working fine. No issues with the code is working fine. However, I would like to test it with multiple cases. For example, you have tested from 2. Let's test it from other vertices also. So let's test it from 1. And I can just give some gap here in between. Like this. How does it look like? Let me look. Okay, I can give one more gap. Like this. Okay. Now, I'm going to do BFS from 1 and let me put it down at the end so it becomes easier to track. Expected output from 2 was this. Similarly, if I talk about expected output from 1, let's write it down. Okay. All right, guys, back to sharing the graph. But before I go there, I need to print g.bfs1 here. Okay. There will print from 1. Let's go back to graph. Let's see if we do a BFS from 1, what is the expected output? Come on, guys, quickly in the chat. What is BFS output starting from the vertex 1? BFS, breadth first search. Quickly in the chat, guys, be quick. Okay. What are the directly connected vertices? Let's start with that first. Directly connected vertices with 1 are what? It's only 1, it's 2, right? 2 is the only directly connected vertex with 1. So if it is 1, 2, well, technical 0, 3, and 1, 2, 3, 0, both are BFS. Yes or no? Come on, guys, quickly in the chat. You go from 1, there are only directly connected vertices 2. So if you go from 2, either you go to 0 or you go to 3, both will become BFS. Interesting part. If you do a DFS from 1, what is going to be the output? Correct. Even if you do a DFS from here, let's say if you go to 2, from 2, you are going to depth anyways, right? So either you go to 0 or you go to 3, that will be the same. So BFS and DFS output can be same as well. Okay. So my expected output is 1203 or 1230. Let's verify if my code is giving me the correct answer or not. We can verify this by code. So I come here, come here. So it can be either 1203 or 1230. Okay, let's run the code. Let's see. 1203, that is the correct output. Okay. How am I deciding 1203, 1230? That depends on the way or the order in which you have added the edges. If you replace the order, let's say if I replace like this, the order will change. Okay. So you can get both the answers at the same time. Okay. All right, guys, that was one. Let's verify from other graphs also, other vertices also. And now I want to verify from 0. Okay. I'll write it down. What should be the output from 0? So we'll go back to graph again. We'll verify the output from 0 this time. All right, we are back here. If you have to start from 0, now what do you guys think would be the BFS output? Quickly in the chat. Not the depth, breadth. BFS, breadth first search. Quickly in the chat, guys. What are directly connected vertices with 0? What are directly connected vertices with 0? With 0, I'm connected with, not this guy, this guy. With 0, I'm connected with 1 and 2. So if I take 0, 1, 2, 3, 0, 1, 2, 3, or I take 0, 2, 1, 3, both of them are BFS output. Agree? Agree? 0, 1, 2, 3 will also become a DFS output. Yes or no? You go from 0 to 1. From 1, you go to the depth of 1, which is 2. And then from 2, you're going to 3. So my DFS output from 0 will also be 0, 1, 2, 3. All agree? Again, BFS, DFS can be same here. Cool. Let's clear it. Let's go back to the Sublime. Let's come back here. Let's see. So 0, 1, 2, 3 or 0, 2, 1. Let's run the code. Let's talk about it. 0, 1, 2, 3. I got the correct output, which is good. Finally, I have one more vertex. Let's cover that as well. If I do my BFS from 3, now what should be the final output? I think this should be straightforward, but let's verify. Okay. All right, guys. Now look at this. What do you think is the BFS traversal starting from 3? If you start from 3, what are directly connected vertices? It's only 3. Now, since 3 has a self edge, if I don't check the condition for true, this will run infinite times. So starting from 3, I cannot go to anywhere basically. No, from 3, you cannot go to anywhere. There is no directly connected vertex with 3. The output will remain 3 only. 2 is not directly connected with 3. 3 is directly connected with 2. Look at the directions. 3 is connected with 2. 2 is not connected with 3. Okay, so come back here. With 3, I should have only one output, which is just 3. So if you run the code now, this is what your output should be. Is my code working correct? Now verified with all the vertices. Now I can say with 100% precision, my code is working correct. Let's take this guy here. Let's come back to Sublime. Go to the code, paste it here, and then print the output. Now I can say clearly my code is working completely fine. Everybody is still clear with this. Come on guys, quickly in the chat. Everybody is still clear with this. Let me save this as Python and then open it because there are too many comments to identify it. Okay. Today is 26th one. Let me save that as well. Okay. Let me open this guy. 26th one. This one we can remove. Anyways, coming back to this. So we got the correct output. The correct output for all the vertices. The code is working completely fine. Okay. Now the important part. How do we define the time and space complexity? By the way, one thing that we can play around with the code is, I haven't done it, but we can play around for sure. It's our code. What will happen if I remove this condition 26? What will happen now? Think about it before giving answer. If I don't check for the condition that a particular vertex has been visited or not, what will exactly happen? Yeah, before going to that part, see, if you're not checking, it will go to infinite loop and eventually it will die out, right? Let's try it out. We shouldn't, but let's try it out, right? Indentation should be here. Okay, the thing about Python is just the indentation, but let's see. Comment this, comment this. Let's see where it takes us. It's running for a lot of time. I'm expecting it to time out. Let's see. Still running, still running, still running. All right. I expected it to be have infinite number of times, and which happened exactly. So we got a time limit exceed, and this is 1308972 more characters, and so many characters running infinite number of times. If you look at this, the first BFS from 2, the first out, forget about going to other vertices, even from 2 also. Can you notice something? 2031, 2320, 3031, 230, 1230, 1230, so on and so forth. Okay. This is how it will go for if you don't put the condition check in. Okay. Anyway, that's just for fun. Don't do that in the interview or while writing the code. Cool guys, can you please explain through Java as if it's new to me? We will go to the code of Java. It's just that I want to make sure that everything is clear in Python first. It's easy to understand and to write. Then we can go to the code of Java and C++. I will go to the code of Java, don't worry about it. But let me complete in Python first because it's easier to explain in Python, it's easier to understand in Python as well. It's just a default dictionary that we are using. Okay. All right. Now coming to this. Time complexity and space complexity of this. Time complexity of graphs, as if you guys remember, I told you yesterday also. Any algorithm that we use on graphs, we don't define the complexity in n square, n cube. There's nothing called n here. It's only the vertices and the edges. So V and E. So time complexity, if I have to iterate a graph or traverse a graph, it's going to be big of V plus E. I will travel all the vertices. I will travel all the edges. Okay. Big of V plus E. That is what you call as time complexity of BFS as well as DFS. Space complexity is big of V. That is what I'm keeping the vertices in a queue. As simple as that. Okay. This part clear to all? Come on, guys. This part clear to all? Quickly in the chat. Time and space complexity. If you want to look at the time complexity here again. So first thing, while Q means you're going for all the vertices. And here we are going for all the edges. So if you have to mention here, this guy is big of V. And then you're going for big of E here. You're going through all vertices and all edges. Space complexity, I'm obviously going to keep big of E here in my queue. All right, that was the first code for traversal, which is BFS. Now, an extension of BFS, and then we'll move on to something next concept. Question number 2, I can say it, or 1, I can say it. BFS for disconnected graph. Now we have seen in a graph, which was a cyclic graph, but it was not disconnected. How will we do BFS for disconnected graph, right? And what, first of all, what is disconnected graph? Let's talk about that first. So I'll take this graph that we have been using so far. I will disconnect it real quick. So there you go. 0, 1, 2, 3, 4. Now in this graph, if I keep my starting vertex as 0, what is BFS output? Quickly in the chat. Starting vertex 0, what is BFS output? Correct. 0, 1, and 3. After that, you traverse whatever you want to. So 0, 1, 3, 2, 4, or 0, 3, 1, 2, 4. Both of them are BFS. This is not a disconnected graph. If I have to make it disconnected, I will write like this. 2 and 5. Now look at this graph, and I'll just remove this cycle also if I want to. Now, if you look at this is something which we call as disconnected graph. What do you mean by disconnected graph? Means in my graph, there are subgraphs which are not connected with each other. In my graph, there are subgraphs which are not connected to each other. So this becomes subgraph number 1, this becomes subgraph number 2. In that case, how would I determine the BFS output? That is interesting. So if I start from 0, 0, 1, 3, 4, right? After that, we add 2 and 5. That is what you call as BFS in a disconnected graph. Question clear to all? First, introduce the concept of disconnected graph means in a graph, if you can divide into subgraphs which are not connected with each other. Repeating it, in a graph, you can divide into subgraph. It can be 10 subgraph, 1000 subgraph, 2 subgraph, whatever that is. Obviously, it will not be one subgraph. If you can divide in more than one subgraph which are not connected with each other, what do you mean by not connected with each other? Between those subgraphs, there is no common edge. So there is no edge connecting it here. There is no edge connecting here. There is no edge connecting here or anything like that. If it is like that, that is what you call as a disconnected graph. Now, what you need to do is you need to do a BFS in a disconnected graph. So output will be 0, 1, 3, 4, and then the BFS of this guy. So output will be 0, 1, 3, 4, 2, 5. Question clear to all? Question clear to all? Any doubt in the understanding of disconnected graph? Come on, guys, be quick. Clear. Okay, if the question is clear, let me know how would you make a code or write a code or an algorithm to a BFS or disconnected graph. No, you're given the starting vertex. Let me put it if it was not given. Starting vertex. Oh, you are saying instead of 2, 5, can I do 5, 2? Is that what you're asking? Yes, you can do that. Okay. For this guy, you can do 2, 5, 5, 2, whatever that is. Yeah, for this one, starting vertex is given as 0. That's the BFS output for that. All right. So this is your question, guys. You have seen the disconnected graph concept. You know how what's the output is going to look like for starting vertex 0. It's okay if you write a code. It's completely okay if you don't write the code. I need a pseudocode or an algorithm that you can explain. If you have to do a BFS in a disconnected graph, how will you do that? Question is clear. We just have gone through the code. One moment, guys, one moment. We just have gone through the code of BFS. If you want, I can give that in the chat. One moment. Holding here. This is the code that we have just written for BFS in a connected graph or BFS in any normal graph. If I give you disconnected graph, how will you modify this code? You can modify this code and give it back to me, or you can change the code, or you can just mention pseudocode. I'm fine with that. What will you do to extend this BFS code to work on a disconnected graph? Okay. Once you guys are done, just let me know in the chat. I think 30 seconds to 1 minute should be a good time for it. Once you guys are done, just let me know in the chat. Please change your message directly to me. Do not message to everyone. Your time starts now. Think about logic for writing BFS in a disconnected graph. or there's enough time. Let's go through what the answers we have got so far. Okay, cool. Some of you have tried to write a code. I can see the bugs in the code. That code won't work. So try to fix the code. But even then, I'm not concerned more about the code. I'm concerned about the approach here. One thing you need to understand, will a simple BFS give me the output for a disconnected graph? Simple BFS means if I take the same code and I try to run it in a disconnected graph, will it give me the correct output? Come on guys, quickly in the chat. Will a simple BFS give the output? No, simple BFS will not give me the answer. Now the question becomes, what will give you the answer? A modified BFS is what will give me the answer. So simple BFS from each unvisited vertex will give me the answer. Okay, let's take an example. I start BFS from 0 here. My output will become 0, 1, 3, 4. Now, once I start traversal from 0, it got 0, 1, 3, 4. So do I need to run a BFS from 1 now? No. Why? Because it's already visited. I need to do the BFS only from unvisited ones. So I won't do from 1, I won't do from 3, I won't do it from 4. Next one is what? Will I do BFS from 2? Is 2 visited? No. So I can do yes. It's not visited. Unvisited vertex. So the output will be 2 and 5 if I do it from 2. Will I do a BFS from 5 now? Do we need to iterate all the vertices? No. You just need to check if it is visited or not visited. Same thing that you are doing here, right? This part. This logic will remain the same. So you're not iterating, but you're checking whether it's visited or not visited. So BFS from 5, do I need to do it? No, because it's already visited. And once everything is visited, what do you need to do? My final output, I need to do 0, 1, 3, 4 dot append this 2 and 5. So this becomes 0, 1, 3, 4, 2, 5. That is a correct answer. Everybody crystal clear with this. You just need to modify BFS a little bit. What do you need to modify a little bit? Just need to check whichever is not visited, you need to run a BFS from there. Whatever is already visited, you don't need to do a BFS there. Time complexity remains the same. I would travel all vertices, all edges as part of my traversal. Space complexity, of course, big of E, because I'll be storing the vertices in a queue. Everybody crystal clear with this? The code of BFS, time and space complexity, and then the approach for BFS in a disconnected graph. Okay. All right, guys. Now let's talk about something interesting. And then we'll do a follow-up question on that. Degrees in a graph. This is an important topic. What do you mean by degrees in a graph? So degrees in a graph, that's a new topic, by the way, nothing to do with BFS and DFS now. We have talked about traversal. We know about BFS, DFS. We have written the code for BFS. DFS code will be writing in some time. Degrees in a graph is a new concept. And this is only for directed graph. So when somebody asks you degree for undirected graph, it doesn't even exist. There's nothing called degree in an undirected graph. Degree as a word only exists for directed graph. Okay. In the degree, we have two different kind of degree. One we call as in degree. One we call as out degree. In degree and out degree. Okay. What are these? Let's go one by one. So I will have 0. Let's make 1. Let's make 2. This, and this. Let's make this. Copy this, paste. It will be 3 here. Then come to here. This and this. It can paste this guy. Nope, too far. Looks good. So now I can have 3 and I can have 4. Look at this graph now. In this graph, let's try to understand what do you mean by in degree, what do you mean by out degree, and why knowing this concept is important. So number 1, in degree. In degree, the word itself says in, means inside. So number of edges for which vertex V is the destination. Number of edges for which that particular vertex is the destination. Or number of edges incoming / merging towards a vertex is what you call as in degree. The number of edges which are incoming or merging towards a particular vertex is called the in degree of that vertex. Okay. Take an example. If I talk about 0, what do you think is the in degree of 0? Quickly in the chat. How many vertices are merging towards 0? Correct. In degree of 0 is 1. There is only one vertex which is merging towards 0. That is 3 to 0. If I talk about 1, what do you think is the in degree of 1? Quickly in the chat. How many vertices are merging towards 1? Okay, somebody said 4. What is the correct answer? Come on, guys, this shouldn't take this much time. Quickly in the chat. The correct answer is 2. The number of edges which are merging towards 1 are number 1, 0 to 1, and what? 4 to 1. These are the two edges. So output becomes 2. This is in degree. Exactly opposite of that becomes out degree. What is out degree? Outwards, going towards outwards. So number of edges for which vertex V is the source, or number of edges outgoing / emerging from a vertex is what you call as out degree. Okay. So number of edges for which vertex V is the source, or number of edges which are outgoing or emerging from a vertex, that is what you call as out degree. Take an example. If I talk about out degree of 0, how many vertices are emerging from 0? Come on, guys, quickly in the chat. How many vertices are emerging from 0? 1. So output becomes 1 here. From 0, I have one vertex. I have one edge which is emerging from 0, which is going from 0 to 1. 0 is the source for this edge. If I talk about 1, what is the out degree of 1? Let's talk about that. How many edges emerging from 1? Emerging from 1. 1 is source of how many edges? Correct. There is only 1, which is 1 to 2. It remains 1, that is 1 to 2. Why are we talking about this? Why are we talking about in degree, out degree? Because there are some really good questions to be solved on top of that, which we'll go to now. But anyways, before I go to the questions, let me quickly revise whatever I discussed so far, and then I can take the questions here. So center of town should have been here, but anyways, this is not added to the list. We'll figure it out. Coming back here. First thing first, we talk about the traversal. We talked about since graph is hierarchical data structure, there is more than one logical way to traverse it. One is called the BFS, one is called the DFS, a breadth first search or a depth first search. To understand that, we got the explanation using trees. So using a tree, we can compare. If I choose to go to depth, that is called the depth first search. If I choose to go to the breadth, that is called the breadth first search. Same we talked about using graph. Now, what do you define as breadth or adjacent in terms of a graph? Directly connected vertices is what you call as breadth. Okay. So if I cover all of them, that is what you call as BFS. If I don't cover all of them, if I go to anything else, that is what you call as DFS. Okay. We took the example, then we moved to an example image. We verified that. We wrote the code. We have verified all the edge cases. all the vertices here. We got the time and space complexity. Then we did a follow-up question for disconnected graph. We got the approach done here along with time and space complexity. Finally, we understood a new concept, which is only for directed graph, which we call as degrees in a graph, in degree and out degree. In degree means the number of edges for which vertex V is my destination, or number of edges which are incoming or merging towards a vertex. That is what you call as in degree. Out degree is the opposite. Number of edges for which vertex V is the source, or number of edges outgoing or emerging from a vertex. Everybody crystal clear with this? Come on, guys, be quick in the chat. Any doubts, any questions so far? All good? So I'm going to do two questions here quickly. I think I should have added to the node, but I don't see it here. So let's directly go it on the lead code, then we'll update it here. Start with question number 3. This is lead code 1791. This is find center of star graph. Okay. Let's go to lead code real quick. Let's start solving that problem. Then we'll come here. Let me open that problem statement real quick. All right, we have got the problem statement getting ready. Okay, very good. This is what we need to solve. Okay, this is lead code 1791. Let's start talking about the problem statement first. So we are clear, then we'll talk about solving it. Find center of star graph. If you look at some of the stats, this has 425.2 thousand submissions. If you look about the companies, good product-based company have asked this question. May not be exactly this question, variation of this question. Concept is same. 1.8 thousand likes, so on and so forth. There is an undirected star graph. We talk about undirected. We know there's going to be, we can go from A to B or B to A, consisting of n nodes. N nodes means n vertices. When somebody says nodes in a graph, means they're talking about vertices. Labeled from 1 to n. Okay. A star graph is a graph where there is one center node and exactly n minus 1 edges. Now, this is important. We got n vertices and n minus 1 edges. There is one center node, exactly n minus 1 edges, that connect the center node with every other node. Okay. You're given a 2D integer array edges where each edge ui vi indicates that there is an edge between the nodes ui and vi. Return the center of the given star graph. Okay. I've given example, let's say 4, 2, 1, 3. So edges are 1, 2, 2, 3, and 4, 2. So 1 and 2 are connected, 2 and 4 are connected, 2 and 3 is connected. What is the center of this star graph? What is the center of this star graph? Correct, 2. Why? Because 2 is connected with everyone. That's why it is become. Another important part, n nodes, n minus 1 edges means n vertices, n minus 1 edges. This part clear to all? N vertices, n minus 1 edges. This part crystal clear to all. Okay. If everybody is clear, now another important part, which I want to discuss another question, but we can discuss it here also. The question itself said it's an undirected star graph. In the first line, they have said it's undirected star graph, right? So that becomes, that makes your life easier. You don't have to worry about whether it's directed or undirected. In some of the question, it will not be very explicitly mentioned. You need to be smart enough to know that. What do I mean by that? Read this statement and tell me if you know about it's directed and undirected, read the statement and what decision can you make out of it? 30 seconds quickly. Just the statement that I have highlighted. From this statement, can you make a decision even if you don't know that whether it is directed or undirected? Quickly answer in the chat. 30 seconds, guys. All right, guys, enough time. What's the answer? Just by reading the statement, can you come to a decision? Yes or no? Can you come to a decision? The answer is yes, you can come to a decision. Read it properly. Given a 2D integer array edges where each edge ui comma vi indicates that there is an edge between the nodes ui and vi. If it was a directed graph, it will say indicate there is an edge from ui to vi. Agree? If it was directed, it will tell you it will be an edge from ui to vi. That indicates that it's a directed graph. If it says there is an edge between the nodes ui and vi, means there is no direction involved. There is no from, there is no to, there is no direction involved. Means it's an undirected graph. Lot many times it will not be mentioned as clear as mentioned here. Okay, especially in the online assessment questions. So you need to be smart enough. You look at the problem statement, you can predict whether they're talking about directed graph or they're talking about undirected graph. As simple as that. Okay. Anyway, this is undirected graph. This is the center of the star graph. Example number 1. Example number 2, I've given the diagram here. So edges are 1, 2, 5, 1, 1, 3, 1, 4. So 1, 2, 5, 1, 1, 3, and 1, 4. What is the center of this star graph? Quickly in the chat. Correct. The center of this star graph is 1 here. Okay, so the output becomes 1. Constraints are given. My number of edges will be from 3 to 10 raised to the power 5. Edges length will be n minus 1. Edges are, or vertices are number of n. Edges length will be equal to 2. Obviously, it's u to v or v to u, whatever that is. U to v or u comma vi will be between 1 to n and ui is not equal to vi. What does this denote? Ui is not equal to vi. What does this denote? Come on, guys. Ui is not equal to vi. What does this denote exactly? Correct. There is no edge which is connecting the same vertex. So there is no self edge. Okay. Given edges represent a valid star graph, so you don't need to worry about what if a test case comes, there is no star graph. So the question has said the given edges always represent a valid star graph. So there will not be a test case where there is no star graph. Okay. Another important part. Why is the minimum number of vertices are 3 here? Why is the minimum number of vertices 3 here? Quickly in the chat. Come on, guys, be quick. There's a reason behind everything. Why the minimum number of vertices needs to be 3. Understand one thing. Simple maths knowledge. If I give you 2 vertex, or forget about it, let's start with 1 vertex or 0 vertex. If I don't have any vertex, can it be center? No. If I have 1 vertex, can it be center? No. If I have 2 vertices, can it be center now? No. Because for the center, it needs to be connected with all other vertices. So it needs to be n minus 1 edges. If I have 3 vertices, now I can call this as a center. Agree? If I have 3 vertices, then I can call it a center. And anything after greater than 3 vertices, I can call it a center. But minimum, I need 3 vertices in order for one of them to qualify as a center. All agree? Okay. Star graph means all other nodes are connected to one node. Yes. Or there can be child node which are not directly connected to one node. No. Star graph means all other nodes are connected to one node. That's what the star means. Okay. All right. If everything is good, let's clear this. Let's close this guy. Let's take the problem statement on Sublime Text first. Then we'll talk about solution. Copy this. Go back to Sublime. We are back here. Example 1. Go to example 2, so on and so forth. And we can mention about the problem statement here. This was one of the first problem statement, by the way. Anyways, I'll talk about this example that we have here so far. understanding. And then we have the function that we have to complete. Let me bring that as well. One moment. Okay, cool. This is the function that we have to complete. This public integer find center. Answer will always exist. You can assume that. Then we'll talk about how do we solve this question. Anyways, so you can look at the function. It says find center. You're given the integer as this, basically a 2D array, which is representing a graph. What you need to do is you need to find the center of that graph. That's it. We'll write the code in Java, so don't worry about the people who are talking about Java code. Okay. Anyways, problem clear to all. You're given a 2D array, which is representing the edges in a graph, right? In that graph, the test cases will be such that you will always have a center. You need to find that center. Question clear to all? Any doubts? Anything required from my end to clarify the question better? Come on, guys, be quick in the chat. Question clear to all? Give me clear in the chat. Any doubts? Any questions? Let me know. All good? Everything looks good? Could you please explain again in Java how edges will be presented? Edges will be presented, same case. Same case. 1 to 2, 2 to 3, 4 to 2. So graph of u dot append v. Same case. Whatever we do in Python, same thing, because eventually this will be a list, right? So if you convert this with the array list, graph of dot get u dot add v. Same thing. Okay. All right, guys. Now coming to this part. Problem is clear to all. Let me give you the problem statement. There goes your lead code question. Link of the lead code question. There goes your function that you have to complete. Feel free to code in any language, and please do mention the time and space complexity along with the code that you are submitting. You guys know the drill. Directly go ahead, submit it on the lead code. Once you guys are done, share that submission link with me. Do mention time and space complexity. It's important for this question, every question for that matter. And once you guys are done, just let me know in the chat, then we can go for discussion. Your time starts now. Change your message directly to me. Do not message to everyone. Once you are done, just update me in the chat. All right, guys, enough time. Enough time. Let's start discussing the answer. Okay. All right, I've seen most of your code, but before we go there, let's talk about something. Anybody needs more time before I move to the solution? Anybody still coding, they need more time, let me know. Okay. All right, guys, now coming to the solution part, I think I've already given enough time for this one. We have other questions to cover as well. What is the best time complexity in which you are able to solve this question? You can message to everyone now. What is the best time complexity you are able to solve this question? Quickly in the chat. Okay, big of one. What about other folks? Anybody else in big of one? Okay, that is the correct answer. I see some of the code where they're coding in big of n, which is fine, but this code can be easily, this question can be easily coded in big of one complexity, and that is the most optimized solution you can think about. Let's start with how do we go to that big of one approach. Start with the intuition, then we'll move to the code part. Intuition is when we say star, right? Star means a center node, which we are calling a star. It must appear in all edges. This is important to understand. See, if there is one node or one vertex which is going to be the center of a graph, means it should be present in all the edges. For example, take this for 1. So 1, 5, 1 is present. 1, 2, 1 is present. 1, 4, 1 is present. 1, 3, 1 is present. So that vertex which is present in all the edges would be my star vertex. Take an example. 1, here it is 2, 2, and 2. So the output becomes 2. It is 1, 1, 1, 1. That's why the output becomes 1. So that particular vertex, which is common in all the edges, that would be my star vertex. This statement crystal clear to all? Yes or no? That vertex, which will be common in all the edges, that is going to be the star vertex. Any question in this? Come on guys, quickly in the chat. All agree with this? Okay. So here we come. A vertex which is common in all edges, that is going to be my answer. Now from here, there are two ways. A brute force way is that I can go for all the edges, and from the edges, I can check whichever is the common. The time complexity is big of V. I'll go through all the edges. Now the optimized solution. Do I need to go through all the edges and I compare which particular vertex is common? Maybe no. And that's something which is going to help here is this part. If you look at this, the constraint has told you very clearly. There are going to be at least 3 vertices and the number of edges are going to be n minus 1, whatever number of vertices minus 1. So minimum edges length is going to be 2. Yes or no? If there are 3 minimum vertices, let me write here. If minimum vertices becomes 3, then minimum edges length will be 2. Yes or no? Come on guys, quickly. At least there will be 2 edges. At least there will be 2 edges. So if I know there will be 2 edges, and there will be more than 2 edges for sure in every test case, first 2 edges will always exist. That is as per the constraint. So what is the optimized solution? If I know that there is going to be only n minus 1 number of edges, and I know that first 2 edges will always exist, I don't need to check in all n edges. I just need to check in the first 2 edges. First 2 edges, I find the common vertex, and that's it. That would be my center of the graph. Center of the graph. I don't need to go through all the edges. Just take the first 2 edges, and that will give your answer. Time compressed is big of 1. Why? Because it cannot be more than the required number of edges. Number of edges is always v minus 1. So it's not possible that I have to iterate more than the first 2 edges to see if there is any other edge existing. Not possible. Okay. Take an example. If I have A, I have B, I have C. B is the one which is star here. So I will write it like this: A comma B and B comma C. B is the common vertex here, which becomes my center of the graph. Minimum edge is 2 and Minimum vertices 3. Everybody crystal clear with this first before I go to the next part. Everybody crystal clear with this first. All good, easy. So we know that the minimum number of edges will be 2. I just need to look up in the first 2 edges, whatever is the common, I'll give my answer. That's it. That's all you have to implement. So let's go to the code real quick. Let's see the solution in big of 1 complexity. I'll take the chat here. Here we are. This is where we go. So this is find center. I'm returning an integer. This is my integer array of edges. What do I need to do? I first initialize a star vertex equal to -1. I just need to check which edge is common. So obviously either it's going to be 0, 0 or it's going to be 0, 1. So if 0, 0 is common, I set the answer to 0, 0. If 0, 1 is common, then I set the answer to 0, 1. Simple. I just need to check whichever is common. And there is not going to be any self edge, so I don't need to take care of that condition. Simple. Time comps to big of 1, space comp to big of 1, you got your answer. And this is the most optimized solution. Compile this, run it. So if you look at the submission, it will beat 100% of the submission. Obviously, its time complexity is big of 1. It's big of 1. And if you look at space complexity, space comp is big of 1 too. It is the most optimized solution. So let's remove it here. Let's take this guy and bring it back to the chat here. There you go. All right, guys. Any doubt, anything which is not clear on this question, let me know. Anything which is not clear in this question, let me know. Everything is good, just type me clear in the chat. First question, or question number 3 technically, finding the center of the star graph. All you need to do is, you need to just analyze in the first 2 edges, whichever is the common vertex, that is going to be the center. Come on guys, quick in the chat. All clear? Okay. This was question number 3. Let's move on to the next question that we have in the sequence, and they'll be using in degree and out degree concept. So let's move to question number 4. Lead code 997. This is find the town judge. Let's start with this. So let me go to the problem statement. Okay. All right. Just sharing my screen. Here we are. This is the next question that we have. Lead code 997. This is find the town judge. And this is a good question. Important one. If you look at the submission, 1.3 million submission, out of 1.3 million submissions, only 49.8% acceptance rate, less than 50% submission get accepted. If you look at the companies, all the good major product-based companies, you can find it here. Now let's go to the question here. In a town, there are n people, labeled from 1 to n. There is a rumor that one of these people is secretly the town judge. If the town judge exists, then the town judge trusts nobody. Everybody except for the town judge trusts the town judge. There's exactly one person that satisfies both properties 1 and 2. Okay. You're given an array trust where trust of I is equal to A of I, B of I, representing that the person labeled A of I trusts the person labeled B of I. If a trust relationship does not exist in trust array, then such a trust relationship does not exist. Return the label of the town judge if it exists, if it can be identified, otherwise return -1. Okay. Now, one thing before I go to next part. Do you notice this line representing that the person labeled A of I trusts the person labeled B of I? Only with this statement, this question has nowhere said it's a graph. This question has nowhere mentioned it's a graph question. In the previous question, they very specifically said it's a graph, and that's how the problem will be in online assessment. They will not tell you that it's a graph. You have to figure out which data structure to use by the problem of the structure, right? This question never said it's a graph, but obviously you can see 1 to n, and then there's some condition, and A of I, B of I. You can make a good sense it's a graph question. But most importantly, this line that I've highlighted, representing that the person labeled A of I trusts the person labeled B of I. Is it a directed graph or is it an undirected graph? Quickly in the chat, guys. Just by reading this problem statement, is it a directed graph or is it an undirected graph? Come on, guys, this should not take this much time. Be quick. Cool. That is correct. This is going to be a directed graph. Why? If it was an undirected graph, this would have shown person labeled A of I, or if it's representing the relation where A of I and B of I trust each other, something like that, right? If it was undirected graph. But it specifically says it's going from A of I to B of I. There is a from and there is a to. That is why it's a directed graph. Okay. Now let's look at the problem statement. We got n equal to 2 and trust relation is 1 to 2. So 1 trust 2. What are the properties of a town judge? Town judge trusts nobody. Everybody else except for the town judge trusts the town judge. So in everybody else, only 1 is there. 1 trusts 2. 2 doesn't trust anyone. Output becomes 2. Example number 1, why 2 is the town judge? Everybody clear? Example number 1, why 2 is the town judge? Everybody clear? Yes or no? Come on, guys, be quick. Okay. Example number 2, n equal to 3, trust becomes 1, 3, and 2, 3. So 1 trust 3, 2 trust 3. Properties of a town judge? Everybody else except from him or her trust them, and they don't trust anyone. So output will become 3. Town judge becomes 3. Example 3, n equal to 3, 1 comma 3, 2 comma 3, and 3 comma 1. Now 1 trusts 3, 2 trusts 3, and 3 trusts 1. Is there any vertex which everyone trusts and they don't trust anyone? Is there any vertex like that in the test case 3? No. So the output becomes -1. There is no town judge here. 1 is not the town judge, 2 is not the town judge, 3 is not the town judge. If you remove this edge, now 3 will become the town judge. Okay. Constants are given. It's going to be 1 till 1000. So number of vertices are going to be minimum 1 till going to 1000. Obviously, it's going to be trust dot length. So it is going to be 0. It can be empty or it can go up to 10 to the power 4. Trust length will be 2. All the pairs of trust are unique. And A of I is not equal to B of I, means there is not going to be any self-edge. A of I, B of I will be less than the number of vertices. Let me take this problem statement. Move it here. Example 1, example 2, example 3. I'll take this here, paste it here. And this was the second question that I was going to cover. Let's bring it here. Okay. Coming to this now. And we got an understanding here. This was our understanding of the question. Okay. Anyways. Solution, and before solution, I'll give you the function that we have to complete. The function that we need to complete is this, that is straightforward. Integer find judge. In the judge, we are given the graph, which is 2D array, which is trust, and we are given integer, which is number of vertices. Okay. Any doubt in the problem statement? Any question in the problem statement which you are not clear, and I can help you with that. If the question is still clear to all, there is a graph which is given to you. Just by the problem statement, you can understand it's a directed graph. In the directed graph, what you need to do is you need to find vertex, which is a town judge. How do you find the town judge? Two conditions. Town judge will not trust anyone. Everybody else will trust the town judge. That's it. Example we discussed here. In this case, everybody else apart from true trust 2. That's why 2 become town trust. Everybody apart from 3 trust the town judge. That's why 3 becomes town judge. Here, there is no vertex which everyone trusts and they don't trust anyone. That's why there is no town judge. So it's -1. Any doubt, anything which is not clear in this question, let me know. If everything is clear, just type clear in the chat. Come on, guys, be quick. Is the problem statement clear? Okay. If everything is good, let's do one thing. This is your lead code link. There you go. And this is the function that you have to complete. You guys know what to do. Directly go down lead code, start solving in the language of your choice. Once you guys are done, just let me know. Please do mention time and space complexity along with the code that you are writing. Share the submission link with me. Once you guys are done, just let me know in the chat. We can discuss. All right, guys, change your message directly to me. Do not message to everyone. Your time starts now. All right, guys, enough time. I think I'm giving enough time. Let's start discussing the solution. Okay. I saw 14 of you have given the answer. What about the rest of you? What about the rest of the folks? Cool, guys. This should not be this difficult question. Let's start thinking the right way and then we can come up to a solution. The answer lies in this part. The two condition. First, when you say, let me remove this, let me remove this, let me come here. When you say everybody except for the town judge, trust the town judge. What does that mean in terms of in degree, out degree? Everybody except for the town judge trust the town judge means in degree for the town judge is going to be n minus 1. Yes or no? Whatever the total number of edges, the in degree for the town judge is going to be n minus 1. There are going to be n minus 1 vertices which are going to be emerging towards the town judge. This part clear? Come on, guys, quickly in the chat. Okay. Number two, when you say the town judge trusts nobody, means the out degree of the town judge is going to be what? It's going to be 0. Yes or no? In degree will become n minus 1, out degree will become 0. So the difference between in degree and out degree will become n minus 1 minus 0, which will become n minus 1. Everyone agrees with this, yes or no? Okay. What does my approach become now? I have this trust of I, which is denoting A of I and B of I. And that denotes A is connected with B. The statement says it's a directed and unweighted graph. All I need to do is I need to find out the difference of in degree out degree to be n minus 1 and then I need to code it. And there can be only one vertex which can just justify this criteria of in degree minus out degree difference and minus 1. Okay, let's go to the code. Let's write down how we can write that code. We are back to lead code. Let's quickly look at the code now. What are we doing here? We just need to know one thing, which is that the difference between in degree and out degree should be n minus 1. So first thing, I create an array called trust score and I'm going for all values. Initially, I'm initializing all the values to be 0. First, I calculate the in degree and out degree. So for out degree, whatever vertex, whatever edge goes out of my out degree, whatever vertex, whatever edge goes out of my vertex, I'm marking it as minus minus. Whatever edge will go inside the vertex, I'm doing it plus plus. Okay, just so compare in degree and out degree. Now the difference of in degree and out degree has to be n minus 1. So I will check if the trust score of I becomes n minus 1, that is when I return I. If I'm not able to find that, I'm going to return minus 1 here. Simple. The important part here is how I'm calculating in degree and out degree. You can do by other things also. I'm not saying this is the only way. You can initialize all the in degrees to be 0, out degrees to be 0, then you can do it. But I find it easier to do it in the terms of subtracting and addition. So differentiate between out degree and in degree. Anything going out of the vertex should be negative. Anything going inside the vertex should be positive. And then you compare the difference if it reaches n minus 1 or not. Okay. If you compile the code, there you go. And if I submit it, this will pass all the test case. Okay. Time complexity, of course, big of n, v plus e, not n. And space complexity, big of e, the number of vertices I'm doing here. Okay. Let's look at this code. Let's come back here. Here's the complexity. Here I'm going big of v, and here I'm going big of e. So complexity become big of v plus e. And what am I doing? I'm storing all the vertices here. So this will become big of v, space complexity. Have a look at this code. Any doubts, any questions, please let me know. Come on, guys, quickly in the chat. Any doubts, any questions, anything which is not clear, let me know. All good? Cool. Let's take this piece of code. Let's take it here. Bring it back. Time complexity, big of v plus e, space complexity, big of V. We are storing all the vertices. And one example of this, if you want a dry run, I already had it. This is a dry run for this one. For n equal to 3, where I have 1, 3, and 2, 3, you can see the town judge is 3. If you look at the difference between the in degree and out degree, that is going to be n minus 1, which is 3 minus 1, which is 2. Okay. All right, guys. Any doubt in this question, code, approach, complexity, please let me know. Any kind of doubts, any kind of questions, any follow-up required, please let me know. If everything is clear, type clear in the chat. All good? All right. If everything is good, let's do a quick revision so far. Okay. Let me come here and I'll also tell you what is pending in terms of questions. So this mark is done. This part is done here. We would need one more class and I'll just mention what we need in the next class. We just need to cover spanning trees, which includes minimum spanning tree. And then we need to cover shortest distance that we can cover as part of one session. Okay, this is something that we would need. Anyways, we'll see when we can schedule the next class and then we'll cover these two topics. But as of now, let's quickly revise what you've done as part of today's session and any question I'm happy to answer, then we'll close the session. First, we started our session with understanding about traversals. Being a graph, it's a hierarchical data structure, so there's more than one logical way to traverse, BFS and DFS. First, we made an analogy using trees. How do we BFS, DFS in trees? And similar, we do it BFS, DFS in graphs. The only point is, how do we determine a breadth? The breadth is determined by the directly connected vertices or adjacent vertices. So we have seen the example here. We read the BFS and DFS output. We talked about the difference between trees and graphs. So that's why we need to keep either an edge, a Boolean array, or you can keep a set here. Then we refer to the image, we write the BFS, DFS output here. Then finally move to the code part. And in terms of the code, we verified it. We verified for all the edges, for all the vertices here, time constant big of E plus E, space constant big of E. Then we move to question for BFS for disconnected graph. We extended the approach. The only thing is that I would need to run a BFS from every unrelated vertex and then need to combine them together. Then we talk about the concept of degrees, which is in degrees and out degrees, which is only defined for directed graph. Then we do two lead code question. First was the find center of star graph. It's a good question. We talked about the optimize approach. Rather than checking on all the edges, I can check for the first two edges. So I can solve this question in time comes to big of 1, space big of 1. And finally, the last question we did, which is find the town judge. So town judge, this is a directed graph. In this directed graph, I need to find that vertex, which is going to be where in degree of that vertex is going to be n minus 1 and the out degree is going to be 0. So the difference between in degree out degree will be n minus 1. We write the code to calculate in degree out degree. Wherever difference become n minus 1, return the code. Time constant big of v plus e, space constant big of v. This is what we have discussed in the question. Can you explain 2 in judge and again? What do you mean by 2 in judge? I didn't get the question. What's the question about 2 in judge and again? Down in judge and again. Okay. You're asking me to explain the question or explain? I didn't get it. Like, what do you want me to explain? Okay, let me explain the question again. Maybe that's what you're looking for. See, the question says there is a town judge. Town judge means everybody else will trust him or her, but he will not trust anyone. Solution of it. Okay, problem is clear. Let's go to the solution. What I'm saying about the solution, if you look at the problem statement, that itself tells you the solution. If everybody except for the town judge does the town judge, means the number of edges which will be incoming towards the town judge, that is what we call as in degree, that will be n minus 1. If total number of edges are n minus 1 edges will be there. Okay. Similarly, the town judge trusts nobody. So number of edges going out of town judge will be 0. So out degree of town judge is going to be 0. So difference between in degree and out degree is n minus 1. That's all I'm doing in the code. So I go to the code, I go to each and every edge. If you look at this edge, at each and every edge for this particular vertex, I am subtracting 1 for in degree, I'm adding 1 for out degree. So subtracting 1 for out degree and increasing 1 for in degree. At the end, I'm just going to each and every edge. These are 1 to edge, these are my edges. I'm going to each vertex. I'm checking for any vertex if the difference is n minus 1. If it is n minus 1, that is actually my town judge. Otherwise, I return minus 1. This is what I'm doing in the code. And I've written the tyrant part here also. So if you look at this, 3 is the one which is going to be a town judge. So in degree minus out degree difference is 3 minus 1, which is 2. And there is only one vertex which can satisfy this condition. If it exists, it's going to be only one vertex, otherwise minus 1. Have a look at this code. Let me know any doubts, any questions. If it requires a dry run, I can do a dry run also. Okay. All right, that's it for the today's session, guys. We would need one more session. Quiz problem, maximum heap, greedy algorithm, tries. Tries is not in the syllabus, but if you want me to cover, we can cover it as part of a doubt clearing session. Queues, max heap, min heap, greedy algorithm. Any specific questions, let me know. Greedy, I think we already know about what does greedy work for. If there's any question that you want me to cover, anything that you are stuck at, let me know. I can take off that. You guys also have your mentor classes, right? If I'm not wrong. You guys should be assigned with a mentor, right? If you are not able to resolve by then, let me know. Then I will pitch in. Usually these personal doubts that you have or any specific questions that you have, mentor are the right person for it because instructor usually take the classes which are like more collective questions, right? All right, sounds good. Cool, guys. One session will definitely need for covering the spanning trees, MST, and the shortest distance. I will ask your course coordinator to schedule the same, but I should be fine. Okay. All right, guys. Thanks for joining it on a national holiday and wish you again for a Republic Day. Let's catch up in the next session, wherever that will be. It will be scheduled and then we'll connect again. Okay. All right, guys. Thanks for joining in. Have a good day. We'll connect in the next session.